Okay, so welcome everybody. Today is December 6th, and greetings actually from Wallops Island out here at the Super Darn radar this week. That's for Wallops Island and doing some repairs and maintenance for it. So a little bit of change in scenery you might notice for me. But otherwise, just wanted a quick plug for the Space of ET YouTube channel where this seminar and others will be posted. Because I have ones. I think I've caught up now. I had a little bit of a delay because I got kind of behind on some work, but we now have ones for all the semester posted there, and so you can review them if you miss this one or miss one in the future, we'll try to have those up there in a decently timely fashion. But otherwise, won't keep everybody here too much. I know we're in the end of the semester crunch, and everybody's people who have classes are trying to finish those out, and people who are teaching classes are also trying to finish those out without too much hassle and too much work, whatnot. But yeah, so today we have a PhD candidate, Shane Coyle, who's been working with the MIST group and is going to talk to us about a problem they've been having with some of their clocks here in the last year or so. So without further ado, go ahead and take it away, Shane.
Thanks, Kevin. Yes, my name is Shane Coyle, and the title of this presentation is MIST and a Problem with Clocks. The Magnetosphere-Ionosphere Science Team, that's the MIST group, Antarctic Geoscience, and remotely troubleshooting bad clocks. So I hope to address each of these questions in this talk. Who is MIST? What is an AAL-PIP? How does an AAL-PIP work? What makes it tick, quite literally? And why shouldn't I take clocks for granted when it comes to embedded systems and remote locations, or just in general? So first, the Alpip, or Autonomous Adaptive Low Power Instrument Platform. Alpip is a series of magnetometer stations rather, in Antarctica. We've got 6 of them currently, with plans to expand 2 more. And I say it's a magnetometer station, but we also include dual frequency GPS at select locations and an HF experiment as well. It's unique in that it's conjugate to a chain of magnetometers in Greenland, which Tom is well representing here, along the 40th magnetic meridian. And so that allows you to do interesting studies on the way the geomagnetic environment changes in both the north and south hemisphere, and contrast the 2 hemispheres. The platforms are entirely solar powered, battery operated, so there's no moving parts, less chance of things breaking that way. So here's a map of the, you can see my pointer, the Greenland chain, the conjugate Antarctic chain, and then the plans for expansion along this route to give us a fully 2-dimensional array as opposed to just the linear chain. So a little bit about our history. This is a project that's been going on since the mid 2000s. Initially started out at University of Michigan, then transferred to Virginia Tech. The first station was deployed in 2008 and is still running, very strong. It's arguably our best performing station. The full 6 stations have been operating since 2016, with the last refurbishment occurring in January 2019 at PG4. So let's talk about the instruments, right? At each of the 6 stations, we've got flex-gate magnetometers. Most of them are the LEMI 22 models. They sample at 1 hertz, which is a pretty standard these days sampling rate for magnetometers, the modern magnetometer stations. We also have 4 search coils at 4 different stations listed there, PG2 through PG5, that sample at 10 hertz. Data is gathered daily from each of these stations. And I'll say that's during the summer season, and that's the austral summer season. So that's typically from late October till about April timeframe. The measurements are taken from October until the batteries run out, which happens, at varying times depending on your latitude. Typically, the stations will last until late until July, sometimes into August, and even we've historically seen them run into early September. So our HF radio experiment is also at 4 of the stations. It's an investigation of the mesoscale communications and in the Antarctic. Some of the details about our transmit modes and power setup. Shown here is a plot of the basically a message error rate contrasted with a proton flux observed by the GOES geostationary satellite. This is GOES East, I think. So it's close to the magnetic field line that the stations would be sensing. And so you can see there's a dropout in the message receive rate that's associated with these proton fluxes here. So some interesting work there. Also some interesting work with the dual frequency GPS. That's the CASES instrument developed by Astra. We've got 4 of these as well, used to measure ionospheric scintillation. We are transitioning them into a more of a TEC-based measurement platform. So more consistent measurements at a lower data rate, kind of spreading them out over the entire local time sector. They typically operate for 2 or 3 months because they do generate a lot of heat, and you wouldn't think that heat is a problem in Antarctica, but we've got a very well insulated box, and generating too much heat can cause us to actually exceed our overtemp thresholds. So I've got here just a list of some recent publications and coming from this instrumentation platform or using our data or by some of the scientists associated with the MIST group. So feel free to contact me for some interesting reads later on. So all that established, let's talk about clocks. It's the meat of our presentation here. Some background on the technical details of our platform. We're using a single board computer to control all of the instrument gathering processes, communications, run the whole gambit. It's the Technologics board shown here. It is a Debian-based Linux system. And if you are familiar with Debian and its releases, I think the current release is version 10, it's Buster, which came out in 2019. Our single board computer runs Debian Ham, which I had to look up, was released in 1998. So it's a little long in the tooth, but it is a very compact, very easy to use operating system, being that it is a Debian Linux package. So how do we interface with this device, right? We use the Iridium Rudix satellite communications network. If you're not familiar with Iridium, it is a global coverage constellation of 70 some odd satellites, provides pole-to-pole coverage. We, with the Rudix network, get a blazing fast 2400 baud TCP/IP connection that we then use for SSH and for file transfer to the remote system. On board that Linux device, there are RPC interfaces, remote procedure call interfaces for each sub-process that manages the different instruments, the housekeeping, and there's a command line interface to execute RPC calls to each of those sub-processes. So our typical operations, daily, the systems will call home every 30 minutes, and that's home to a server at Virginia Tech. There's an auto downloader that will initiate a file transfer on daily occurrence. Usually, I think it starts at 4 a.m. UT. And then after sundown, like I said, the austral summer, once the sun goes down, only housekeeping data is retrieved. We still collect all the magnetometer data, all the instrument data, but that's once the sun goes down, we keep all of that stuff on board until the following season, where we generate a listing of the backlog data and then collect that data from when the sun was down. So now we'll kind of switch gears and talk about clocks in Linux, specifically in our system. This is a very oversimplified slide explaining how clocks work in Linux systems. I mean, this could really be a talk in and of itself, but basically you've got two clocks, right? You've got a hardware clock, which is commonly the real-time clock. It's a monatomic. Effectively it's a incrementing counter, right? And you just count from 1 until the highest number you can count to, and then you start back over. And it's based on, if it's internal to your CPU, there's, you might just have that counter literally just every time the CPU cycle goes, it just increments. Or you might have some other piece of hardware, an extra peripheral on the board, like an external RTC that's got its own battery power, it's got its own crystal oscillator. You've got a phase lock loop to keep synchronized, and then you do some frequency mixing to get your clock signal. So that's the hardware clock. It's rarely interfaced with at the kernel level or at the user level rather, inside the Linux operating system. It's just there to basically keep time between powering off and powering back on your system. Now your system clock is the clock that everyone's far more familiar with. It's the software-based clock. It's the highest level clock. It's it's time zone dependent. Even if it's storing the information in UT, it has that information associated with it. It can be adjusted freely, and it's you can think of it as just some number of milliseconds, microseconds, nanoseconds, whatever, since an epoch. For Linux systems, it's January 1st, 1970. So to compare and contrast them, think of the hardware clock as a flip-flop. You've got a latched gate there that toggles on and off, and that's what's being counted. Whereas the system clock has got a lot more information into it. It's some number of seconds or some measure of time since an epoch, right? The system clock is the one, and I'm not saying that anyone would have done this or has any experience with this, but if you've ever, tried a trial software and you found yourself 2 weeks later after the trial expired needing to go back and reuse that software, the system clock would be the one that you change in order to get that software to work. The hardware clock is still going to effectively tick the same way. So that aside, let's talk about our time synchronization procedure on the Alpip systems, right? So, you power up the system. The first time we get power to the board, all of the different software starts, right? And so for time synchronization purposes, we enable our GPS module on board, wait for the GPS to get a fix to synchronize with the network, and then we adjust the date and time. Now, this is the system clock that's being adjusted at this point, right? And it's being synchronized to whatever the GPS module is reporting. The drift rate is then fixed based on GPS readings every hour, right? So GPS provides you with a 1 Hertz, very stable reference frequency. You can figure out, how many clock ticks have occurred on your local hardware compared to the GPS reference, and then figure out how many clock cycles occur within a second and make some adjustments. Now, why wouldn't we just have GPS on all the time and use that forever? It's a very power hungry device, surprisingly. You think, your GPS is in a watch or something like that, and your watch lasts all day, but we've got 1,600 amp hour batteries, car lead acid batteries that are sitting in the snow, powering this thing for months. The GPS is actually, I think, a 50% of our power budget whenever it's on for our systems. So I think it operates at 1 watt, and our board operates at 2 watts max. Typically, it's at 1 watt. So it's only on for a little bit to get that synchronization, and then it turns off. So now we've got a reliance on GPS established. Let's talk about what happened in April 2019. GPS navigation data uses a 10-bit week number. If you're not too familiar with the technical details of that, that means that the week number counter will overflow after 1024 weeks, which is approximately 19 and a half years. The most recent occurrence was in April of 2019, the previous one in the year 2000. The next one will occur in November 20th of 2038. Interestingly, in 2038, we'll also be running into a different clock rollover occurrence. The Unix 32-bit signed integer representation of time elapsed since 1970 will occur on January 19th, 2038. So thing to watch out for if you're not aware of it. But this GPS rollover. So let's imagine what happens to our Alpip system whenever the GPS module updates, right? So I've got the kind of timing diagram of the procedure here. We boot up at some time t0. We set the system time to that t0. We open the Iridium link. We start a watchdog timer. We turn on the GPS module. Eventually, the GPS module will synchronize, and the GPS time is whatever UTC is minus 19.6 years, because our rollover has occurred, and we're back at week 0 of the epoch, right? So week 0, according to a GPS module, is whatever the week 0 of that epoch is, which is 19 and a half years ago. So once that synchronization occurs, we then set the system clock to that time, and all kinds of wacky stuff happens. So when the system rolled over, when GPS rolled over in 2019 April, nothing really happened because this synchronization only occurs immediately after boot up, and the systems boot up several months prior to April. They boot up in October, and ideally they don't ever turn off. So this step right here, where we set the system time to the GPS module time, never happens. All we do is our drift rate adjustments, which is based on a reference frequency and not any actual time. So in April, nothing dramatic happens. The problem occurs the following season whenever we go through this whole process and we do this step. So the clock is adjusted to boot up. The watchdog is waiting for a system time to reach 24 hours after boot. That 24 hours is after it boots up this clock based on the hardware time, but it's checking the system time. So it's actually waiting for 24 hours plus 19 and a half years before it will recognize a communications fault and reboot the system. Conveniently, our Iridium link also has a similar fault that occurs because of this kind of out of order synchronization and clock turning back whenever you're not supposed to. So in mid-November 2019, after the systems had come back up from our hibernation, usually in September, we panic, right? We've got 4 of 6 stations with no communications. Measurements are disabled because internally we disregard measurements that don't have accurate timing or a good timing reference. So thankfully, at this point, after just a moment of panic, we are able to troubleshoot the software, the hardware, the whole setup on a local spare system that we have available. With some help from another grad student, Yisheng Peng, we are able to replicate the GPS fault in our spare system, identify exactly what happens, exactly what behavior is causing this fault, and come up with the fix. So the obvious fix is, well, if the GPS time is 19 and a half years wrong, then add 19 and a half years to it and problem solved. And so that's what we do, but that's a Band-Aid fix. It's going to work until 2038. And hopefully between now and that point, we'll be able to get out there and physically upgrade these systems, refurbish them, and find smarter, better ways to mitigate this kind of an issue. One of those ways we kind of already have in place is to utilize an Iridium network as a timing backup. If GPS reports a date time that's way off of whatever is being reported by the hardware clock, which is accurate, but drifts around, right? If it's something more than 2 months off, right, then we know that the GPS is providing a suspect date. And so you can fall back to the other satellite network that you have access to, the Iridium network, request timing information from them. It's less accurate than GPS. It's something like, less than 100 milliseconds, but somewhere around that range. So it's not the nanoseconds that GPS offers, but it's accurate enough for our science. So that's the software fix that we designed. Then it came time to implement it. In January of 2020, we were able to get a team out from NJIT, New Jersey Institute of Technology, to one of our sites, PG0. And they had a little bit of difficulty getting the GPS antenna off of the system. They were able to turn the system off. There's a power box right there, and climb the tower. The idea was to disconnect the GPS, run the system. That would allow us to communicate with the system at the very least. It won't synchronize with the satellite network and then roll back the clocks. We could then use the established Iridium link to update the software. But because of difficulties disconnecting the GPS antenna, and because being out in the deep field in Antarctica is not a luxury that you can, you can't just spend all day out there and laze about. Weather is a big concern for flights out there. Fuel is scarce. They have to have caches and depots buried in the ice. You have to make multiple hops to get out to any of these sites. So eventually we were running out of time. We decided, well, let's just cut the GPS cable, turn the thing back on, and hope for the best. It didn't impact this specific site because this specific site doesn't have the dual frequency GPS. It doesn't limit any of our instrumentation. We were able to use the Iridium timing as our backup timing for the magnetometer measurements. And before they even touched down in South Pole again, we were able to get the system up and running nominally. So with that one use case of our software update working, we decided, okay, great. We've got good success. We can plan site visits for Austral Summer 2020. We won't cut the GPS next time. We'll just turn it off and give ourselves a little more time. And then COVID happened. And so no one could go to the deep field in Antarctica. Very few people were able to go to Antarctica at all. So support becomes very limited. Field visits become very unlikely. We are in a situation where we're going to have to suffer for another year of potentially not having half of our stations working, right? The spark of insight here that saved us is the realization that at the very beginning of the season, there's a small window of opportunity, about 40 seconds to 90 seconds long, where the system is powered on. It has an open communications link, but it hasn't achieved GPS synchronization and set the clock back. So if we remember our timeline here, it's this little window right here between these steps that we're counting on. So we tried to utilize that. We wrote a script on the VT server that checks for an active call from each remote system, and immediately within 2 seconds initiates an SSH connection. Bear in mind, we are using Iridium 2400 baud network. This takes about 20 to 35 seconds to just SSH into the system. The script will then kill the remote GPS manager process, disabling any kinds of attempts to set the clock back or do any of that other wonky stuff. It renames the GPS driver, which effectively uninstalls it, and prevents our watchdog from taking a 20-year nap. So fingers crossed, we found out it worked. We had that script running this October, and within an hour or so of the first system making its first attempts to connect, we were able to get it, the GPS disabled. We were able to then give ourselves a little bit of breathing room. We could do a software update at our leisure. Did the software update to adjust the GPS, and everything has worked. Each system that's woken up so far has been updated. They're all, all the ones that have woken up are working. They're all updated. They're all working perfectly. We're at 5 of 6 stations currently. And we didn't have to wait until the 2021 field season to potentially get out to one of the sites and fix it. So this remote software update ended up being a whole lot less expensive and working a lot quicker than relying on personnel getting to a remote site. So with that, let's talk about some lessons learned, and I guess we'll open it up for discussion after that. But I think from our experience, we can say a couple good things. First, communications are a vital system in remote systems design. Software updates are cheap compared to site visits, as I just said. If you're a member of a CubeSat team or something to that effect, site visits are pretty much out of the question. So you need to have you need to do your due diligence when it comes to communications systems. If you're a controls guy, if you have a controls background, communications is your control. It's your feedback, right? Close the loop. That's the ticket to having a reliable system design. Software timers are not reliable, and I say that maybe it's kind of a harsh statement, but they're fine for things like file attributes, logs, things that aren't going to stop your system from working or aren't going to brick it. But something like a watchdog, which is ideally your last line of defense against erroneous system behavior, really needs to be on something more reliable and less interfaceable, right? Hardware timers, monotonic clocks, things that you don't reset or change really ever throughout the procedure of operating your system are really the way to go for designing watchdogs. Another interesting bit, modules can have hard and soft failures, right? So the GPS module worked, kind of. It didn't turn off, right? It didn't give us any kind of power faults or anything like that. It was providing data in the correct format. There was no issues with the way GPS was reporting its values. It's just that the values were bad, right? It was misinterpreting the signal that comes from GPS and providing us with bad data. So, that's something to consider, is that your modules in your global system design are not always going to be either on or off, right? Sometimes they can just be wrong and on, right? So that's something to look out for. Single points of failure are a huge thing to look out for, right? In our system, GPS was a single point of failure, right? Not only would it potentially give us this fault whenever the GPS is providing the wrong value, but it would also, if it wasn't enabled, block measurements, right? We weren't able to collect data, and effectively that turned an Alpip into a very expensive thermometer. So having the ability to fall back onto a redundant system like the Iridium network for timing is paramount in these kinds of remote system designs. Kind of going hand in hand with that, single points of failure and avoiding them is doing extensive integration testing, right? I don't think anyone really expected GPS to fail, right? GPS is one of those things that everybody really takes for granted. And I mean, I know I certainly did prior to finding out what the details of how they oriented their weak numbers and sent that data. So, these are all things that, basically you don't ever want to take any of your systems for granted and figure out, just expect them to always work, right? And then, lastly, keep a spare tire handy, right? We probably would still be at a point of developing solutions. Maybe not, but it would have definitely been a much bigger headache to develop a software fix and then implement it had we not had test hardware on site at Virginia Tech. Now, we don't have duplicates of all the instrumentation and all the expensive devices. We just have a very simple, the single board computer, the power routing board, and a couple of the other electronic bits. It's not always feasible to build a second thing that you're designing. But if you can get away with simulating some of it and build part of a second thing, or find some way to replicate your hardware through simulation, that is incredibly important, because nobody can predict everything that will go wrong with your system. So having something you can pull out of your pocket and figure out whenever things go wrong unexpectedly is an incredible boon. So with that, I think I'll open it up to questions, comments, concerns.
Well, certainly, thank you very much, Shane. Thank you. Open it up for anybody with any questions.
How much battery power were required to provide year-round operation?
I've done this calculation before, and I can't remember exactly. I think if we had another 600 amp hours, we could span that. So I'll tell you, our systems currently operate, from early March, second week of October until July-ish, right? So depending on your latitude, if you're at the pole, high latitude, right, you get a little bit less sunlight. I think for that station specifically, if we had another 600 amp hours of batteries, then we'd be able to get full year coverage easily, right? Part of the other aspect to this is, the batteries get colder, right? During the austral summer, it's about -30°C inside the battery pit. As the sun goes down and as we spend less and less energy heating the batteries, they get colder. And so, as they freeze, they're able to provide less charge. So that said, we have currently 16 of those 100 amp hour batteries. So you're looking about, 2,000 amp hours, I guess that would be.
Yeah, but I guess
each node has 2,000 amp hours.
About, yeah. Now, that said, there are other things that we could do to extend our life, potentially. Reducing that amount of call time back to our home server from half an hour to an hour, or say every 2 hours or something like that. That impacts our operational capacity, right? We aren't able to provide as great maintenance, as timely service to the systems. And because it is Rudix, it is a mobile originated service. We aren't able to call our stations. We have to wait for them to call us. But there are things that we could do to potentially lower our consumption throughout the year.
How much energy are required to have the batteries heat themselves using their own power?
Sorry, say that. Could you say that again?
I said, how much energy would it require to have the batteries heat themselves to from their own power? You say they get colder, they lose efficiency. I was wondering if they had their own heaters, how would that work? Would that help?
Right. Yeah. So we do have heaters in there, and that's something they engage above a certain, or rather below a certain temperature threshold. But they also have a voltage shutoff. So your heaters won't engage whenever you're deep into the austral winter, where you have limited capacity to heat yourself, right? Because you're going to get diminishing returns as the as time goes on without any ability to replenish charge. So haven't gotten the math on all of that handy, but I can definitely forward that to you if you're interested.
Okay.
Yeah, and that kind of speaking to seeing parts of the system change, there's some trickiness with that too, because as you would add more batteries, right, I think you would have to add more heaters probably, and so you have kind of a positive feedback loop kind of thing, that the more batteries you add, the more heaters you have to add, so the more batteries you have to add, and so on.
Yeah, definitely. Well, it's definitely a balancing act.
It would it probably involves some calculus. It sort of becomes the problem sort of becomes equivalent to if you have a rocket and you're trying to launch payload. Eventually, you have, depending on the distance, you have more fuel to launch the payload to orbit. But as you add more fuel to it, you have to have more fuel to launch more fuel, basically.
Yeah, it's definitely an optimization problem waiting to be solved there.
Yeah, I'll just chime in one quick comment on that. I mean, one thing that is interesting that we could look at in the future is using something like windmills. I know some groups are, they've had issues with them in the past because it's mechanical, there's moving parts, but potentially we could look at that. Maybe just keep it, it's not like the power supply for the system, but maybe it could just power the battery heaters or something like that. So anyway, we might explore that in the future, alternative power sources.
Yeah, Antarctica is interesting in that it has gravity-powered winds. Just one of the things that the Antarctica science people were saying.
Yeah, it's definitely an interesting and unique environment to operate in, providing all kinds of interesting challenges. So
actually, gravity-driven winds, I think they're called.
So I had a question going back to the timing part. You said that you've had good success with the script that you've written. Do you have like a good, this is not intended to be an interesting, or just a play on that, but a good handle on, I guess, how narrowly you've been able to get into that, or how much time you've had, what's the I don't know, not that anybody's watching, but the stress point of like seeing the countdown clock kind of going thing, and how much time's left before you are able to I guess snip the red wire in the software.
Yeah, so I did a little bit of testing on the benchtop system. Having it here and being able to just turn it on and let it go through its boot up process and get a GPS fix. And it's about a 10-second, 15-second wiggle room. With the script running, that was part of the process of deciding, how often I should pull for the connections for the remote systems. And I figured 2 seconds gave us enough wiggle room where if something kind of goes wrong, or if we get an invalid packet or something on the initial checksum, then we can recover from that. Yeah, so it's about 15 seconds or so wiggle room that we give ourselves. And that's by design. That's
Okay, yeah, because like I say, with such of the success criteria, I'm sure you've for the success rate, I guess, is you've tested. I was just wondering, if you've been able to see it in real time with the ones that you have, implemented this fix, or with uninstalling it. But what's the kind of how much time you've had left on it. But yeah, it's very good, and certainly too, I think it's interesting. We've sort of talked with this too, about how very surprisingly with these kinds of systems, it's almost like you are doing a spacecraft design, right? And some of the parts, I think that single board computer is very spacecraft design oriented. But even down to something that's common in the spacecraft building world of having the engineering unit, which is what you guys had basically, was what was the engineering unit, and going back to it to troubleshoot it, kind of thing.
Yep. Yeah, exactly. That's lots of spacecraft type board layouts, right? PC 104s and all that other fun stuff. And yeah, having that spare on hand was a lifesaver in this process for sure.
What kind of batteries were you using? I think I missed that.
I couldn't tell you the brand name. I think maybe PowerSonic comes to mind, but they're lead acid.
Lead acid, okay.
Yeah, they're it's pretty much.
They're an AGM.
AGM, okay, yeah. Yeah, that's about your best option in that kind of environment, where they're going to be buried and at minus 30 C at the warmest.
Plus, you want to cycle discharge on them.
Exactly, yeah. So there's hopefully some of the newer lithium-based technologies are able to address some of their difficulties at low temperature, and we can move to that kind of technology in the future. But based on our research and the two systems that we're expanding with are lead acid based as well. So that's kind of the state of the art, I'd say.
What are you using to insulate the stuff with?
So the battery boxes are they're just insulated with, I think, maybe it's either 2 or 3 inches of polystyrene. And then the electronics boxes are insulated with that same amount of hard foam, and then I want to say it's a 6-inch thick vacuum sealed panel, and it's comes in 2 parts. It's got a lid and the 6-inch cube basically with a cutout for the electronics. And it's actually, I think, maybe too much for our system. I did mention the cases instrument provides a lot of heat when it's operating. It's it's got its own digital signal processing board and some other RF electronics on it. And we, our main concern when running that instrument is heat inside of the box. So I think we could probably stand to reason or stand to strip some of that out and maybe get better performance in future iterations.
I was just wondering if you guys considered using the Dewar technology for the batteries or whatever, because some of those Dewars to handle cryogenic liquids can handle have really low heat transmission.
Yeah, one of the major issues with getting these systems up and running in the Antarctic is simply the logistics of it. And those 16 lead acids are a pretty big burden as it is, hopping on all those small little flights. I think I forget what the aircraft model number is that gets out there, but we don't have a lot of wiggle room when it comes to carrying a bunch of extra equipment out there. So that's one of our major considerations operating in the deep field.
Okay, well, Dewars also have a tendency to be fragile because they're vacuum glass and all that.
Right, yeah.
Or, yeah, glass with a vacuum. But of course, if your electronics are overheating, you can always try to ventilate some of the heat to the surrounding atmosphere outside to at least temporarily bring in a little bit of cold to it, or have some sort of thermal transfer.
Right. Yeah, that's something I've thought about is how to potentially gate a thermal transfer mechanism through that insulation and turn it off whenever I don't want it. Then we start running into potentially adding a significant amount of complication and power issues, moving parts, things that can fail. So it's an interesting problem that we have. Even something as simple as moving the electronics box into co-locating it with the batteries so that the heat from the electronics warms the batteries might be an efficient solution. So
Yeah, I was thinking that as well.
I guess getting back to the timing thing, trying to belabor this with too many questions. I guess it's an interesting thing that both the GPS time and the epoch time are going to roll over in the same year, though I guess they're at least a little bit spaced apart in the year, but I guess we'll really not know what time it is in 2038.
Yeah. Well, so I didn't mention one of the systems that was, I think it's PG5, didn't succumb to this rollover issue. And it's one of the newer systems that has the same GPS module, but that module was bought several years after the initial deployments. And so the current thinking is that the module that we received for that system had an updated firmware that was able to handle the rollover event. Another thing too, some of the newer, more fancy GPS modules that are using the CNAV data as opposed to just the regular nav data, they utilize a 13-bit week number. So, that's not going to roll over for, I think, 150 years or something to that effect. So much more leeway when it comes to rollover events on more modern hardware, but it's something to be aware of if you're trying to build a low cost, low power instrument platform or several platforms, right?
Yeah, it's very, very true. So any other questions here in particular with what Shane's presented for us today?
Actually, you could maybe try Stirling engine coolers. They have low moving parts that might help to vent some of the heat from the inside to the outside.
Yeah, I hadn't thought about that. I guess that's something to look into for sure.
Maybe like some on submarines because Stirling engines, because they don't make any noise, and that's a very large consideration for that, for stealth operations. But they can be used to convert heat to mechanical power. They can also be used in reverse to convert mechanical power to cooling, but they have very low moving parts. I think NASA was proposing to use it to cool a rover on Venus because that's put up with a 900-degree, 90 atmosphere environment.
Yeah, that's definitely something to look into. Yeah, that's very interesting.
Okay. Any other questions? One last call here. Give the brief second for people to unmute if they're trying to, but not hearing anything. So thank you everybody for joining us. We'll see if we can try to do something. We might do something a little bit special next week about this time, but I'll see if we can put something together. Otherwise, again, this is our last kind of seminar for the semester. We'll be putting together the schedule for next semester in the spring. I think we've already got a company that's looking to, maybe a special one that'll be actually a company that'll be trying to present to us towards the end of January or beginning of February. But otherwise, it's completely open. And so if anybody has a topic that they want to join us and share with the group, you're welcome to it. And certainly too, just like Shane, for the students that participate and present, be entered into. Oh, sorry, I'm in a room that has a auto timer thing that turns the lights out. It happened once during, and that's funny that while I'm talking, it happened again. Anyways, I was saying for the students, they will be entered into a consideration for a $2,500 award for the best in engineering and best in space science for topics that are presented here. So, so again, thanks everybody. And if we don't talk to you, hear from you next week, have a good holiday break. And we'll be talking to you in probably a month and a half or so. So, see ya.